In 1935, Albert Einstein presented a thought experiment that revealed something shocking about the fabric of reality itself. He demonstrated that quantum mechanics violates one of the most fundamental principles in all of physics, the cosmic speed limit, the absolute rule that nothing can travel faster than the speed of light. The physics community didn't want to believe him. They assumed the great Einstein, now in his mid-50s, had lost his edge. Perhaps he was simply too old, too rigid, too stuck in classical thinking to accept this radical new framework that was rewriting the rules of nature. But 3 decades later, a physicist stumbled upon Einstein's nearly forgotten paper and realized something extraordinary. The prediction Einstein had made wasn't just theoretical speculation. It could actually be tested in a laboratory. When scientists finally performed the experiment, the results sent shockwaves through the physics world. Quantum mechanics genuinely does break the universal speed limit. We are forced to accept that something, some kind of influence or connection, appears to travel faster than light itself, bridging vast distances instantaneously. This is the story of one of the most profound and widely misinterpreted experiments in the history of science. And it might just be the strongest evidence we have that our universe is far stranger than we ever imagined. Some interpretations even suggest it points toward the existence of parallel realities, multiple worlds branching off with every quantum measurement. Imagine for a moment that our sun suddenly vanished, blinked out of existence, without warning. How long would it take before we noticed? How long before Earth, no longer held in its gravitational embrace, went spinning off into the cold darkness of space? According to Isaac Newton's theory of gravity, the answer is immediate. Gravity, in Newton's formulation, acts instantaneously across any distance. If the sun disappeared, we would feel it right away. The gravitational pull keeping us in orbit would cease in that same moment. But Newton himself was deeply troubled by this implication. He found the idea philosophically disturbing, even absurd. The notion that one body could exert a force on another across the emptiness of space, with no medium or mechanism connecting them, struck him as fundamentally wrong. He wrote that the idea of action at a distance was so great an absurdity that no reasonable person could accept it. Yet his equations worked beautifully, predicting the motions of planets and moons with stunning accuracy. So the theory persisted, absurdity and all. Then, in 1905, Albert Einstein changed everything. He didn't just find action at a distance philosophically troubling. He showed that it leads to genuine logical contradictions, actual paradoxes that make the theory untenable. Einstein had discovered something revolutionary about time itself. He realized that observers moving at different speeds experience time differently and can fundamentally disagree about when events occur. If you witness 2 events happening simultaneously, someone speeding past you would see those same events in a different order. One would happen first, then the other. And crucially, both perspectives are equally valid. Neither observer is wrong. This is the relativity of simultaneity, one of the strangest predictions of special relativity. But when you apply this insight to Newton's theory of gravity, disaster strikes. Imagine you see the sun disappear and Earth simultaneously fly off into space, exactly as Newton predicted with instantaneous gravitational action. Now, consider an observer moving at high speed relative to you. From their frame of reference, they would see something impossible. They would see Earth break free from its orbit first, while the sun still exists, still exerting its gravitational pull. To them, it would appear that the Earth escaped before the cause of its escape occurred. Effect would precede cause. The arrow of time would reverse. The only way to resolve this paradox is to abandon the assumption that created it. Gravity cannot be instantaneous. There must be a delay between cause and effect. It took Einstein an additional decade of intense work to solve this problem completely, and in the process, he revolutionized our entire understanding of gravity. His solution was general relativity, a theory that reimagines gravity not as a force at all, but as the curvature of space-time itself. Massive objects like the sun warp the fabric of space and time around them, and other objects move along the curves in that warped geometry. When something changes in this gravitational field, when the sun hypothetically disappeared, that change doesn't instantaneously affect distant regions. Instead, it creates ripples in space-time that propagate outward at a finite speed, spreading from one location to the next until they eventually reach us. This is what physicists mean by locality. Effects spread locally, from point to adjacent point, at a maximum speed set by the speed of light. If the sun vanished, we wouldn't feel it for about 8 minutes, the time it takes light to travel from the sun to Earth. Different observers might disagree about the exact duration of the delay due to relativistic effects, but now everyone agrees on the order of events. The sun disappears first, then later we feel the consequences. Causality is preserved. The paradox is resolved. This is why nothing can exceed the speed of light. That finite delay between cause and effect is what ensures all observers agree on which came first. It's the foundation of causality itself in our universe. After Einstein completed general relativity, all of classical physics respected this principle. Every force, every interaction obeyed locality. The universe made sense again. But then Einstein turned his attention to a new theory that was emerging, a theory called quantum mechanics, and he discovered something terrifying. This elegant, fundamental principle was about to be shattered. One of the most iconic photographs in the history of physics captures a moment in 1927 at the Solvay conference in Brussels. The image shows the greatest minds in physics gathered together. The architects of quantum theory assembled to debate its meaning and implications. Roughly 60% of the people in that photograph would eventually win Nobel Prizes. But Einstein believed they had made a catastrophic error, and he was determined to prove it. He took the stage with a thought experiment designed to expose what he saw as a fatal flaw in quantum mechanics. Picture this. You fire a single electron through a narrow slit toward a circular detection screen. According to quantum mechanics, this electron doesn't travel as a simple particle following a definite path. Instead, it has a wave function associated with it, a wave-like entity that spreads out through space as the electron moves. When the electron finally strikes the detection screen, you detect it at a single point, one specific location. The probability of finding it at any given spot depends on the amplitude of the wave function at that location. Where the wave is large, detection is likely. Where the wave is small, detection is unlikely. Suppose the electron appears at one particular point on the screen. So far, everyone in the audience followed along. This is exactly what quantum mechanics predicts. A wave function that spreads out, then a detection at a single location. But then Einstein asked a question that caught them off guard. Why doesn't the electron appear at a different location a moment later? There's only one electron, so we can't detect it twice. But the way quantum mechanics ensures this is striking. When the electron is detected at the first location, its wave function instantly collapses to zero everywhere else. The probability of finding it anywhere else immediately becomes zero. There's no longer any wave at those other locations. But Einstein pressed the audience to think carefully about what this really means. The measurement at one location must instantaneously affect the wave function at every other location, no matter how far away. Even if parts of the wave function have spread to opposite sides of the laboratory, or opposite sides of the galaxy for that matter, they all collapse at once. Quantum mechanics, Einstein argued, requires instantaneous influences across arbitrary distances. It violates locality, the very principle that took him 10 years to restore when fixing Newton's theory of gravity. Einstein concluded by calling this an entirely peculiar mechanism of action at a distance. He argued it represented a fundamental contradiction with the theory of relativity. His talk was so brief and his argument so deceptively simple that the audience didn't quite know how to respond. One prominent physicist, Niels Bohr, admitted afterward that he didn't understand what point Einstein was trying to make. Bohr thought perhaps he himself was missing something, that the confusion was his own fault. But Niels Bohr was not just any physicist. He was the most influential figure in quantum physics at that time. His institute in Copenhagen had become the center of the quantum revolution. Young physicists from around the world came to study under him. One of his students later recalled how Bohr would invite groups of them to his home, where they would sit close to him, some literally on the floor at his feet, straining to catch every word he spoke. This wasn't just education. It was almost a form of discipleship. Bohr wasn't the mathematician who formulated the equations of quantum mechanics. That work was done by others, like Heisenberg and Schrödinger. But Bohr told everyone what those equations meant, how to interpret them, how to think about them. While other physicists struggled with the strangeness of the theory, Bohr offered answers. His philosophical framework became known as the Copenhagen interpretation of quantum mechanics, and it dominated the field for decades. The Copenhagen interpretation says this: the wave function describes everything that can be known about a quantum system. It evolves smoothly according to the Schrödinger equation. But when you make a measurement, something different happens. The wave function collapses, jumping discontinuously to a single definite outcome. Bohr insisted that the wave function is the complete description. It's wrong to ask what the electron is really doing when you're not looking. That question doesn't even make sense. Physics, according to Bohr, isn't about discovering how nature truly is. Physics is simply about predicting the results of measurements in laboratories. And quantum mechanics does this extraordinarily well. What more could you want? Einstein despised this interpretation. In a letter to his friend Erwin Schrödinger, he called it a tranquilizing philosophy, almost like a religion designed to avoid asking difficult questions. Einstein felt his thought experiment had revealed a critical weakness. He'd shown that wave function collapse is non-local, requiring instantaneous effects across distance. So perhaps, Einstein reasoned, the problem is the wave function itself. Maybe it's not the best way to describe reality. Maybe there's a deeper theory underneath, one that respects locality. Einstein may not have convinced Bohr during his talk, but the conference lasted several days, and Einstein was determined to continue the debate. However, the story that's usually told about what happened next isn't quite accurate. Physicists often recount that Einstein challenged quantum mechanics by proposing thought experiments designed to violate Heisenberg's uncertainty principle, and that Bohr successfully refuted each challenge. Eventually, the story goes, everyone agreed that Bohr was right and Einstein was wrong. Case closed. But this narrative appears to be misleading. We now have documented evidence that suggests Bohr may have simply misunderstood what Einstein was arguing. In at least one recorded case, Einstein described a thought experiment involving a box of photons and a mirror. The purpose was to demonstrate the non-locality of wave function collapse. But when Bohr later recounted this experiment to others, he drew a diagram of Einstein's setup that didn't include the mirror at all. The core element was missing. Yet this was celebrated as Bohr's great victory over Einstein, which is remarkable when you think about it. But as the saying goes, history is written by the victors. To understand what Einstein was actually arguing, think about the relationship between Newton's theory of gravity and Einstein's general relativity. Newton's theory works extremely well in most situations. Its predictions are accurate for almost everything we observe in everyday life. But there's a problem. Gravity in Newton's theory is a non-local force, acting instantaneously across space, which leads to paradoxes. This observation motivated Einstein to develop general relativity, which is local and paradox-free. Einstein believed the same logic applied to quantum mechanics. His thought experiment demonstrated that quantum theory is fundamentally non-local. Therefore, just as with Newton's gravity, quantum mechanics cannot be the final theory. There must be a deeper, local theory that will eventually replace it. And as a bonus, Einstein hoped this new theory might even unify quantum mechanics with gravity, providing a complete description of nature. When you see apparent paradoxes or internal tensions in a theory, it's reasonable to suspect there's more to discover, something missing. But Einstein hadn't even succeeded in convincing Bohr that quantum mechanics was truly non-local. So in 1935, he decided to make one final, decisive attempt to demonstrate the contradiction between quantum mechanics and relativity. With the help of two younger colleagues, Boris Podolsky and Nathan Rosen, he formulated an even more striking thought experiment that made the non-locality impossible to ignore. This paper is now known simply as EPR, after the initials of its three authors. Here's a simplified version of what they proposed. Imagine a high-energy photon that spontaneously transforms into two particles, an electron and a positron. This process must conserve electric charge. Since one particle carries negative charge and the other carries positive charge, they cancel out, giving the same total charge as the original photon. But electrons and positrons also have another property called spin, and this too must be conserved. If the initial photon had zero spin, then the two particles together must also have zero total spin. This means if the electron's spin points in one direction, the positron's spin must point in the exact opposite direction so they cancel perfectly. But here's the quantum twist. The electron's spin could be pointing this way, or that way, or any number of other ways. All of these possibilities are valid according to the rules of quantum mechanics. And crucially, quantum mechanics says the electron isn't secretly in just one of these states. It's genuinely in all of them simultaneously until a measurement is made. This is superposition. The only requirement is that whatever the electron is doing, the positron must be doing the exact opposite. When the electron is measured and forced to pick a specific state, the positron's state is immediately determined as well. The two particles are entangled. Their states are correlated, dependent on each other, even though they're separate objects. To measure these particles and force them into definite states, we use a device called the Stern-Gerlach apparatus. It's essentially a specially shaped magnet that deflects particles based on their spin. The orientation of the magnet determines which axis you're measuring. For instance, if you set up the apparatus to measure spin along the vertical axis and send in a particle with positive spin in that direction, it will definitely deflect upward to a spot we'll call plus. If you send in a particle with negative spin, it will definitely deflect downward to a spot we'll call minus. Now, what happens when you put one of your entangled particles through this apparatus? Since the particle is in a superposition, it could go either direction. Let's say when you measure the electron, it goes upward to plus with 50-50 probability. This measurement forces the electron's wave function to collapse from being in a superposition to having definite positive spin. But what about the positron on the other side? The only way to conserve total spin is if the positron is now in the state of definite negative spin. When it's measured, there's a 100% probability it will go to minus. It has to work this way to preserve spin conservation. But the authors of the EPR paper realized something deeply strange about this conclusion. To understand what's so strange, imagine that the electron and positron each carry sealed envelopes with them. These envelopes represent their quantum states. Before measurement, both particles are in superposition, so conceptually, both possibilities exist in each envelope. Now imagine moving the positron far away, perhaps to the other side of the galaxy. In this analogy, opening the envelope is like measuring the particle. When you measure the electron and open its envelope, the wave function collapses to a single outcome. Let's say it's plus. But what happens to the positron's envelope on the other side of the galaxy? It needs to instantly collapse to minus. Otherwise, when the distant experimenter opens their envelope, they might get plus, which would violate spin conservation. But if the positron's envelope must collapse instantly when the electron is measured, how does it know what to collapse to? It must somehow receive information from the electron, and that information would have to travel faster than light to arrive in time. There's no other way to explain it within the Copenhagen interpretation. With this argument, Einstein, Podolsky, and Rosen had made the non-locality of quantum mechanics undeniable. Einstein had already shown this in his earlier conference talk, but this new version was even more compelling and harder to dismiss. The thought experiment was clearer, more concrete, more difficult to misunderstand. It does feel more powerful somehow. Now you have two separate particles in different locations, and one measurement is instantaneously influencing another measurement far away. That definitely seems wrong. It seems like it should violate causality or relativity or something fundamental. And measurements, as it turns out, are precisely where the problem lies in quantum mechanics. That's where the theory becomes non-local. The wave function of a single particle, or of an entangled pair, can spread out over vast distances. That spreading itself isn't the issue. The problem arises when the wave function collapses during measurement. Information about that collapse needs to propagate everywhere the wave function exists, and it appears to do so instantaneously. That's what makes quantum mechanics non-local. But the EPR paper didn't stop at merely pointing out this non-locality problem. The authors went further and proved something remarkable. They showed there exists one and only one type of local alternative theory that could explain this experiment without invoking faster-than-light influences. In this local alternative story, the electron doesn't randomly choose whether to be plus or minus when it's measured. Instead, it makes that determination much earlier, back when it's still in contact with the positron, right at the moment they're created. There's some random process that assigns plus or minus to each particle's envelope while they're together. These predetermined values are called hidden variables because they're hidden from our view until measurement reveals them. And because this alternative theory assigns these variables locally, while the particles are still in contact, rather than across vast distances, we call it a local hidden variable theory. This local hidden variable theory explains the experiment beautifully and simply. Send the positron far away. When the electron is later measured and reveals plus, it doesn't need to send any signal to the positron. The positron already knows what value it has. It was determined from the beginning. There's no action at a distance, no faster-than-light influence. Everything happens locally, respecting the speed limit of light. This local hidden variable story is so much more reasonable, so much more intuitive than the quantum mechanical version. It preserves locality, it preserves causality, it doesn't require mysterious instantaneous influences. It's the kind of theory Einstein believed physics should aspire to. So we're forced to make a choice. We must accept one of two possible explanations for the EPR experiment. Either we accept non-locality, as the Copenhagen interpretation requires, with its instantaneous wave function collapse, or we accept a local hidden variable theory where predetermined values eliminate the need for faster-than-light communication. Given that non-local action at a distance appears to contradict the foundations of relativity, Einstein believed this was definitive proof. The Copenhagen interpretation must be wrong. There must be some local hidden variable theory waiting to be discovered, a deeper theory that will replace quantum mechanics. Einstein had shown us that quantum mechanics permits influences that seem to propagate faster than light. He demonstrated that the theory we were all using had this bizarre, troubling feature built into its foundations. But for decades, this observation seemed to be purely philosophical. It didn't appear to make any practical difference. The EPR paper certainly generated attention. Without consulting Einstein, Podolsky leaked it to the press, and the story appeared in the New York Times. Einstein was the most famous scientist alive, and here he was, challenging the strange but wildly successful theory of quantum mechanics. The press loved the controversy. But what did the scientific community think of the actual argument? The reaction was mixed. Some of Einstein's old allies, particularly Erwin Schrödinger, were enthusiastic. In fact, Schrödinger published his famous cat thought experiment partly to support Einstein and illustrate the kind of problem they both saw in quantum physics. Meanwhile, Niels Bohr was troubled. He seemed to think something must be wrong with the EPR argument, but he struggled to articulate exactly what. Bohr eventually published a response to the EPR paper. This response is famously difficult to understand. The writing is convoluted, the logic obscure. Some physicists who've studied it carefully believe Bohr's reply is either nonsensical or contains actual logical errors. One physicist commented that there's a particular sentence Bohr clearly took great care in formulating, and yet its meaning remains completely obscure. In his reply, Bohr insisted there was nothing non-local happening in quantum mechanics. No faster-than-light influences, no violation of locality. Yet he never clearly explained how this could be, how the EPR correlations could exist without non-local effects. Despite the confusion, the physics community largely sided with Bohr. They believed he had somehow settled the matter, even though few people understood what he'd actually said. Bohr's authority in quantum physics was simply that strong. 2 decades after the EPR paper, Einstein died, still questioning quantum mechanics, still unconvinced by the Copenhagen interpretation. But the majority of the physics community had long since moved on. They had more pressing problems to solve, practical calculations to perform, experiments to conduct. The foundational debates seemed like distractions from the real work of physics. Bohr, however, never forgot about EPR. 7 years after Einstein's death, in 1962, Bohr gave an interview about his old rival. He lamented that Einstein had wasted decades on these fruitless thought experiments simply because he couldn't accept quantum mechanics. It was terrible that Einstein worked with Podolsky on that paper, Bohr said. Rosen is even worse from my perspective. Rosen still believes the EPR experiment reveals something important. Podolsky, as far as I know, has given it up. The whole idea is absolutely nothing. When you really examine it carefully, there's no problem at all. Perhaps I'm saying it too strongly, but it's true. There's absolutely no issue there. The next day, Bohr took a nap after lunch. He never woke up. And so, after many decades, the Einstein-Bohr debate ended. Bohr's immense authority and influence were part of the reason the EPR paper didn't receive the attention it deserved. But there was another, perhaps more practical reason physicists largely ignored it. In the EPR experiment, both theories, both the Copenhagen interpretation and Einstein's local hidden variable alternative, make exactly the same prediction. You get identical experimental results either way. Debating 2 different interpretations that produced the same outcomes seemed like pointless philosophy, not real physics. The Copenhagen interpretation made good predictions. Why not just use it and move on. Why waste time on metaphysical questions? The prevailing attitude became shut up and calculate. Who cares about the interpretation? It's all been settled anyway. Einstein and Bohr had their debate, and Bohr won. Do you think you're smarter than Niels Bohr? Do you think you're smarter than Einstein? The implication was clear. If those giants couldn't resolve it, what hope do you have? Just learn the formalism and apply it. It seemed impossible that this foundational debate would ever be resolved through experiment. The two interpretations gave the same predictions. How could you possibly test between them? It appeared to be a purely philosophical question, forever beyond the reach of empirical science, until another physicist turned his attention to the problem. John Bell was an undergraduate student in the years following World War II, entering physics during this new era when quantum mechanics had become standard. He was naturally taught the Copenhagen interpretation as if it were gospel. But, by his own account, Bell's doubts about quantum mechanics appeared almost immediately, essentially the first time he learned it. In his very first quantum mechanics class, he became frustrated with his instructors, pressing them for clarity. What exactly do you mean by measurement? Why are you being so vague about this? Bell never received satisfying answers to his questions about the foundations of quantum mechanics. During his PhD work, he was encouraged to focus on something more respectable, more mainstream, so he studied nuclear physics instead, and went on to have a distinguished career at CERN, the European Particle Physics Laboratory. But after 8 years of working in particle physics, in 1963, he took an academic sabbatical. Finally, he had time to return to those old doubts that had never left him. As he later said, he always knew the problem was waiting for him. He began by carefully re-examining the old debates, reading the papers that most physicists had long dismissed as mere philosophical distractions. This included the EPR paper. After studying these arguments thoroughly, Bell wrote that he felt Einstein's intellectual superiority over Bohr in this debate was enormous, a vast gulf between the person who saw clearly what was needed and the person who obscured the issues. Bell realized Einstein's logic was sound. One of the two conclusions had to be true. Either quantum mechanics is non-local, or there exists a local hidden variable theory. The question was whether you could prove which one was correct using an actual experiment. Could you design a test that would distinguish between these two possibilities? Such an experiment seemed far more feasible by Bell's time than it had in 1935. The EPR paper was the first to seriously consider entanglement, the quantum correlation between separated particles. In 1935, no one had created such exotic states of matter in a laboratory. Entanglement was purely theoretical, but in the decades between Einstein's work and Bell's, between 1935 and 1964, entanglement had become a serious topic of experimental research. By Bell's era, physicists had reliable methods for creating entangled states. Madame Wu had even successfully reproduced the EPR thought experiment as a real laboratory experiment. However, simply performing the EPR experiment in real life wasn't enough to determine which explanation was correct. Both interpretations predicted the same outcome. You'd learn nothing new, but Bell wondered whether there might be a variation of the experiment, a modified version, where the non-local quantum theory and the local hidden variable theory would have to give different predictions. If such an experiment existed, you could finally settle the question empirically. Here's Bell's crucial insight. If you're working with the EPR setup and trying to find a way to distinguish the theories, you need to introduce a twist, literally. Bell's modified experiment works like this. Create your entangled electron and positron just as before. But now, instead of measuring them along a single fixed axis, the experimenters get a choice. They can choose how to orient their Stern-Gerlach apparatus. Let's say there are 3 possible orientations: 0 degrees, 120 degrees, and 240 degrees, equally spaced around a circle. The two experimenters can choose independently. The electron might be measured at 0 degrees, while the positron is measured at 240 degrees. They don't have to coordinate. They make their choices separately, perhaps at random. If both experimenters happen to choose the same axis, we know what occurs. They must get opposite results to conserve spin. The electron goes to plus, the positron goes to minus, or vice versa. That's the same as the original EPR experiment. The interesting case arises when the experimenters choose different axes. The key quantity we want to predict is the disagreement rate. The probability that the electron's measurement result differs from the positron's measurement result when different axes are chosen. Let's first calculate what quantum mechanics predicts for this disagreement rate. Suppose the electron is measured along the 0-degree axis and the result is plus. The measurement forces the electron's spin to collapse into the positive state along that axis. According to quantum mechanics, the positron's spin must instantly collapse to the negative state along the same axis to conserve total spin. This is the non-local aspect of quantum mechanics, the instantaneous correlation. But now what happens when the positron is measured along a different axis, say 120 degrees? The positron's spin is already in a definite state along the 0-degree axis, but the measurement device is rotated. Because the positron's spin vector is now oriented more toward the plus end of the tilted apparatus than the minus end, it's much more likely to register as plus. The precise calculation shows there's a 75% probability it goes to plus, and only a 25% probability it goes to minus. Therefore, the disagreement rate is 25%, and you can verify that the geometry works out the same way for any pair of different axes the experimenters might choose. Whenever they select different orientations, they'll get the same outcome 75% of the time, and different outcomes 25% of the time. That's the quantum mechanical prediction. Now consider the local hidden variable alternative. Imagine the particles are on a mission. Their goal is to make you believe they're following quantum mechanics when really they're acting according to local hidden variables. This anthropomorphization is actually quite useful for understanding the logic. Picture the particles as agents trying to fool you. The particles need to figure out their strategy. Each particle will be asked one of 3 possible questions, corresponding to the 3 measurement axes. They need to decide on their answers to all 3 questions while they're still together, while they're still in contact, so they can coordinate their strategy. Once they've determined their plan, they pack those hidden variable answers into 3 sealed envelopes for each particle. 1 envelope for each possible measurement axis. The question is, what strategy should our scheming particles use to make observers believe they're following quantum mechanics? Remember, quantum mechanics predicted a disagreement rate of 25%, so the particles want to match that. Whenever they're asked different questions, meaning measured along different axes, their answers need to disagree about 25% of the time. What's the best strategy to achieve this? It turns out there are really only 2 types of strategies the particles can pursue. The first strategy is simple. The electron answers the same way, let's say minus, for all 3 of its axes. The positron answers the opposite way, plus, for all 3 of its axes. But this strategy fails miserably. Whatever 2 different axes the experimenters choose, the disagreement rate is 100%. The particles always give opposite answers. That's nothing like the 25% disagreement rate that quantum mechanics predicts. So, that strategy doesn't work. But there's only one other type of strategy available. Instead of the electron giving the same answer for all 3 axes, it gives the same answer for any 2 of its axes and a different answer for the remaining one. For example, the electron might answer minus for 0 degrees and minus for 120 degrees, but plus for 240 degrees. The positron does the opposite, plus, plus, minus. This is just one example, but it turns out that for all possible strategies of this type, the disagreement rate comes out the same. Let's calculate it. Imagine the experimenter measuring the electron happens to choose the 120-degree axis and gets minus. This occurs 1/3 of the time since there are 3 equally likely choices. To find the disagreement rate, we need to determine what happens when the other experimenter measures the positron along a different axis. They'll choose either 0 degrees or 240 degrees. But looking at the positron's hidden variables, we see it also gives minus for both of those axes. So the 2 measurements agree. There's no disagreement. We can multiply this 1/3 probability by 0 disagreement. But 2/3 of the time, the electron experimenter will choose one of the other 2 axes, say 0 degrees, and get minus. The positron experimenter will then choose one of the 2 remaining axes. Looking at the hidden variables, we see that the positron's answer disagrees only half the time. For 0 degrees, it says plus, which disagrees. But for 120 degrees, it says minus, which agrees. So the total disagreement rate is 1/3 times 0 plus 2/3 times 1/2, which equals 1/3, approximately 33%. This is fundamentally different from the quantum mechanical prediction of 25%. When our local scheming particles are interrogated separately, their answers match just slightly too often. They can't quite fake the quantum correlations. No matter what strategy they adopt, no matter what hidden variables they pack into their envelopes while still in contact, they cannot reproduce the predictions of quantum mechanics for this modified experiment. Bell had proven something extraordinary. Non-local quantum mechanics predicts disagreement 25% of the time. Local hidden variable theories predict disagreement at least 33% of the time. These are different numbers, different predictions, which means you can perform the experiment and find out which theory is correct. You can finally determine whether Einstein's dream of a local hidden variable theory is viable, or whether we're stuck with the non-locality of quantum mechanics. Welcome to the Institut d'Optique in Paris. This is the place where, 40 years ago, physicist Alain Aspect performed groundbreaking experiments measuring Bell's inequalities. The original equipment from those historic experiments still exists here. What Aspect accomplished was extraordinary. A genuine experimental tour de force that was far more challenging to execute then than it would be today with modern technology. The setup looks deceptively simple now. On a small breadboard sits the main source. A beam is directed toward a crucial element, a pair of nonlinear crystals that produce pairs of entangled photons. These photons propagate along two separate arms of the apparatus. At the end of each arm is a detection system, and crucially, there's a wave plate that can be rotated to change the orientation of the measurement basis. This is the experimental implementation of Bell's test. The photon experiment differs slightly from the electron-positron version described earlier, but the underlying logic is identical. First, there's an element that creates entangled pairs of particles. These particles travel along separate paths to different parts of the laboratory. At each location, there's a measurement apparatus that can be independently rotated, determining which axis the particle is measured along. The rotation of these polarizers in the photon experiment corresponds exactly to the rotation of the Stern-Gerlach devices in the electron experiment. Before the first Bell test was performed, John Bell himself expected that quantum mechanics would be vindicated. He said it was very hard for him to doubt the outcome, given the general success of quantum theory. Who would bet against quantum mechanics? You'd have to be crazy. The theory had proven itself again and again in countless experiments. Still, there was that slim possibility that Einstein was right, that local hidden variables would prevail. The experiment measures the disagreement rate just as Bell's theorem requires. First, both measurement devices are aligned in the same direction. In this configuration, the entangled particles should always give opposite results due to spin conservation. By creating many entangled pairs and counting how many register as opposite per second, you get a baseline measurement of the total particle flux, the rate at which entangled pairs are being produced. Then you rotate one of the axes and measure again. Now you count the number of disagreeing pairs per second with this new configuration. Dividing the second number by the first gives you the disagreement rate. And remember, quantum mechanics predicts this rate will be 25%, while local hidden variables predict it will be at least 33%. The experimental results were unambiguous. The disagreement rate matched the quantum mechanical prediction. It was 25%, not 33%. Quantum mechanics was right. The local hidden variable theory was wrong. The universe really does exhibit these strange non-local correlations. But this experiment, despite its clarity and importance, remains one of the most widely misunderstood results in all of physics. You'll find in textbooks, in papers, in countless popular accounts, that Bell's theorem rules out local hidden variables, or local realism. But John Bell himself said this was an error. He noted it was quite remarkable how many people made that mistake, how pervasive the misunderstanding had become. The confusion is understandable. When people first learn Bell's theorem, they're often told it rules out local hidden variables. Full stop. But that's not quite right. Others say it forces you to give up either locality or realism. But what does that even mean? Realism about what, exactly? For most definitions of realism, giving it up would also require giving up locality in some sense. So what are you actually saving? It's a deeply confused way of framing the result, yet it appears in nearly every textbook on the subject. So, what does Bell's theorem actually prove? Let's trace through the logic carefully. Start by assuming locality holds for the entangled particles. Using the EPR argument, The only way for these particles to coordinate their measurement outcomes while respecting locality is through local hidden variables. They must carry predetermined instructions that were assigned when they were still in contact. Then Bell's proof demonstrated that local hidden variables, any theory based on them, cannot reproduce the correct experimental results. They predict a disagreement rate of at least 33%, but experiments show 25%. Therefore, the initial assumption, the assumption of locality, must be false. We are obliged to accept that something like actions going faster than light occur from one place to another. Some kind of influence, some kind of connection, must be propagating faster than the speed of light to explain these correlations. The EPR paper by itself had already shown that the Copenhagen interpretation is non-local. That's why Einstein believed there must be a local alternative waiting to be discovered. But Bell's theorem says that's not possible. Any theory, any explanation that correctly describes this experiment must be non-local. There's no way around it. But does this mean Einstein was wrong? That's worth considering carefully. Yes, Einstein's hope for a local hidden variable theory turned out to be impossible. The universe doesn't work that way. But it would be hasty to say Einstein was simply wrong about everything. What you could say instead is that Einstein was absolutely right to be concerned about all of this. People often claim Einstein's problem was that he couldn't accept quantum mechanics, that he was too stubborn or too old-fashioned to embrace the new physics. But that's a caricature. It was precisely because Einstein refused to shut up and calculate, because he insisted on asking deep questions about what the theory meant, that he discovered two of the most important and profound aspects of quantum mechanics: entanglement and non-locality. The heart of the debate between Einstein and Bohr was about whether there was a genuine problem to be concerned about, something that needed explanation or resolution. The major concern Einstein raised from the very beginning was about locality. And what Bell's theorem showed was that Einstein was completely right to worry about it. There is a problem. Non-locality is real and unavoidable. If these entangled particles really are acting non-locally, influencing each other faster than light, shouldn't this cause paradoxes? Shouldn't it contradict relativity in a dramatic, destructive way? Well, it does create paradoxes, but they turn out to be surprisingly tame, less severe than you might expect. Imagine you and a friend are measuring a pair of entangled particles. One observer watching from a particular frame of reference sees you measure your particle first, then sees your friend measure hers a moment later. To this observer, it appears that your measurement caused the overall quantum state to collapse, determining both outcomes. Your friend's measurement just revealed what was already determined. But another observer, moving at a different velocity, will see the situation completely reversed. In their frame of reference, your friend measured first, and you measured second. To them, it was her measurement that caused the collapse, and your measurement merely revealed the result. Both observers are equally correct. Their perspectives are equally valid. So who's actually right? Which measurement was the true cause of the collapse, and which was the effect? It seems to depend entirely on your frame of reference. Different observers disagree about which event happened first, just as relativity predicts. This is troubling. It suggests the causal structure of quantum mechanics might be frame-dependent, observer-dependent. This paradox is genuinely worrying, but it turns out not to be as catastrophic as the usual faster-than-light paradoxes that plague theories violating relativity. In relativity, if you could communicate faster than light, you could exploit how different observers disagree about timing to create time travel paradoxes. Here's how. If your friend on a fast-moving rocket sends you an instantaneous message, and you immediately send an instantaneous message back, then in some reference frames, your return message arrives before she sent her original message. If your message says, "Don't send your original message," and she obeys, then you have a classic paradox. What caused you to send your message in the first place if she never sent hers? Quantum mechanics avoids these catastrophic time travel paradoxes through a fundamental constraint. The measurement outcomes are random. When you measure your particle, you get plus or minus completely at random. You have no control over the result. Your friend, measuring her particle, also gets a random result. The results are correlated with each other, yes, but they're still completely random. Since you can't control what result you get, you can't encode a message. You can't use this faster-than-light correlation to actually communicate information. There's no way to send signals, no way to transmit data. That's what prevents the time travel paradoxes. You can't send a message telling someone not to send their message because you can't send messages at all. So quantum mechanics is non-local, but the non-locality is carefully constrained. It doesn't lead to the sort of catastrophic logical contradictions you might expect from a theory that violates relativity. Still, it's an uneasy truce. Quantum mechanics may not break the letter of relativity's laws, but it certainly violates the spirit. The elegant locality that Einstein worked so hard to establish in general relativity is undermined by quantum mechanics. And non-locality isn't the only troubling aspect of quantum mechanics. The Copenhagen interpretation still doesn't explain what an electron is actually doing before measurement, or why measurement causes such a dramatically different kind of behavior compared to normal quantum evolution. Despite these issues, many physicists interpreted Bell's theorem as vindication of the Copenhagen interpretation. They thought Bell had proven Bohr right all along, but Bell himself strongly rejected this conclusion. He spent the rest of his life championing alternative interpretations of quantum mechanics, including a hidden variable interpretation called pilot wave theory, also known as Bohmian mechanics or de Broglie-Bohm theory. Bell's theorem doesn't rule out this interpretation because pilot wave theory is explicitly non-local, just like the Copenhagen interpretation. It's only local hidden variable theories that Bell's theorem eliminates. It was Bell's theorem and Bell's subsequent tireless advocacy that made studying the foundations and interpretations of quantum mechanics respectable again. He demonstrated that philosophical thought experiments and foundational questions can have real, measurable consequences. They're not just armchair philosophy divorced from experimental physics. They can lead to actual predictions, actual tests, actual scientific progress. We need to teach quantum physics differently. We need to teach Bell's theorem differently. It's often presented to physics students as something that rules out local hidden variables, end of story. But that's not the full picture. Bell's theorem demonstrates that quantum physics is in serious tension with relativity on the fundamental issue of locality. That's the real lesson. John Bell died suddenly at the age of 62. He didn't know it, but he had been nominated for the Nobel Prize just a year before his death. In a talk he gave in Geneva in January 1990, he said that he believed we're stuck with non-locality. He didn't know any conception of locality that works with quantum mechanics. That was 8 months before he died, pretty much his last word on the subject. And so that's the conclusion. There really are faster than light influences in the universe. Bell's theorem proves it. The experimental evidence confirms it. Non-locality is a real feature of nature, as strange and uncomfortable as that seems. But maybe, just maybe, there is a way out. There's another interpretation of quantum mechanics that's even more bizarre than the Copenhagen interpretation, yet it might resolve the locality problem in an unexpected way. Consider the EPR thought experiment once more. We can think of the entangled state as a superposition. One possibility where the electron has spin up and the positron has spin down, plus another possibility where the electron has spin down and the positron has spin up. Both possibilities exist simultaneously in quantum superposition. In the Copenhagen interpretation, when you measure a particle and get a single definite result, let's say plus, the other part of the superposition vanishes. It collapses away. But we've seen that this measurement collapse appears to be the source of non-locality. The wave function must instantaneously update everywhere, faster than light. So what if we simply eliminate collapse altogether? What if we stop saying the wave function collapses when measured? This is the radical proposal of the many worlds interpretation of quantum mechanics. In many worlds, when you measure a particle, both outcomes actually happen. There's no collapse. Instead, you become entangled with the particle. There's one version of you who sees the plus result, and another version of you who sees the minus result. Both versions exist. Both are real, experiencing different branches of reality. It sounds fantastical, but there's one enormous benefit to this interpretation. When your friend is about to measure her electron far away, your positron doesn't need to send any faster than light signal. There's no need for instant communication. There are already 2 versions of the positron existing in superposition, and each version contains the correct answer for the corresponding version of your friend. In the branch where you saw plus, the positron is in the state that will give your friend minus. In the branch where you saw minus, the positron is in the state that will give your friend plus. Both branches exist from the beginning. There was never any need for faster-than-light communication to coordinate the results. But wait, doesn't Bell's theorem prove that entangled particles must communicate faster than light? How can many worlds avoid that conclusion? The answer lies in a subtle but crucial detail. In Bell's proof, there's an implicit assumption that all measurements have just one outcome, that when you measure a particle, you get a single, definite result. But that assumption simply isn't true in the many worlds interpretation. Every measurement has all possible outcomes, creating branches for each one. This means Bell's proof, technically speaking, doesn't even apply to the many worlds case. The logical structure of the argument depends on an assumption that many worlds denies. So, is many worlds local or non-local? The answer is subtle, almost paradoxical. In one sense, no, it's not local. Just like in Copenhagen quantum mechanics, entangled pairs can be separated by vast distances and still share their quantum state, still remain correlated. There's still something connecting them across space. However, in another crucial sense, many worlds is local, fundamentally different from Copenhagen. These faraway entangled particles do not influence each other faster than light. There's no instantaneous collapse, no faster than light update of the wave function. Everything propagates at or below the speed of light. The theory obeys Einstein's universal speed limit. But is it really worth accepting the existence of countless parallel versions of yourself, branching universes for every quantum event, just to recover locality? Is that price too high? Well, locality isn't the only reason many worlds has been gaining popularity among physicists. Many people find the Copenhagen interpretation unsatisfying for other reasons. Copenhagen says the wave function evolves smoothly according to the Schrödinger equation, but then something completely different happens during measurement. The wave function suddenly, discontinuously collapses. But what exactly constitutes a measurement? When does collapse occur? If you have a quantum system interacting with another, larger system, at what point does measurement happen? At what threshold does the observer become big enough or conscious enough to trigger collapse? These questions feel arbitrary. There's no clear answer within Copenhagen. It always seems somewhat ad hoc, somewhat artificial. In contrast, the many worlds picture feels more consistent, more unified. Every time two quantum systems interact, their wave functions combine and become entangled. There's no special collapse mechanism. There's just the Schrödinger equation operating universally. That consistency is appealing. It feels like a more fundamental description. What are the problems with many worlds? The biggest challenge for most people is psychological. The sheer infinity of branching realities is difficult to accept, hard to wrap your mind around. Every quantum event splits the universe into multiple branches, each equally real. The number of branches grows exponentially, becoming unimaginably vast. But difficulty in accepting something, difficulty in visualizing it, isn't necessarily an argument against it being true. Reality doesn't care whether we find it easy to imagine. The universe is under no obligation to match our intuitions. Just because something is hard to believe doesn't mean it's not what's actually happening. If many worlds is correct, if it's the true description of quantum mechanics, then everything changes. The apparent conflict between quantum mechanics and relativity vanishes. For decades, physicists have struggled to unify quantum mechanics with general relativity, to construct a theory of quantum gravity. We've been failing, making limited progress despite enormous effort. Maybe we've been failing because we've been trying to marry relativity, a local theory, to a non-local theory of quantum mechanics. We've been trying to combine incompatible frameworks. But if quantum mechanics is ultimately local, if many worlds or something like it is correct, then Einstein's dream of a local description of reality isn't dead. The quest for a unified theory that respects locality, that preserves the elegant causal structure Einstein worked so hard to establish, that quest might still be possible. The path forward might require accepting some very strange ideas about the nature of reality, about branching universes and multiple versions of ourselves. But it might preserve something even more fundamental, the principle that effects propagate locally, that causes precede effects, that the universe has a coherent causal structure. Einstein spent the last decades of his life questioning quantum mechanics, searching for a deeper theory. The physics community largely dismissed his concerns, believed he'd lost touch with modern physics, thought he couldn't accept the revolutionary new ideas. But Einstein was asking exactly the right questions. He identified the core issues that still puzzle us today: entanglement, non-locality, the measurement problem. the relationship between quantum mechanics and relativity. Bell's theorem vindicated Einstein's concerns, proved that the problems Einstein identified were real and profound, not just philosophical quibbles. And now, decades later, we're still grappling with these same issues, still trying to understand what quantum mechanics is telling us about the nature of reality. Perhaps there is something faster than light. Perhaps non-locality is a fundamental feature of our universe that we must accept. Or perhaps the many worlds interpretation is correct, and the appearance of non-locality is an illusion created by our limited perspective, our inability to see all the branches of reality simultaneously. We don't yet know the answer. The question remains open, one of the deepest mysteries in all of physics. But we've learned something profound. The universe is stranger than we imagined. Reality operates according to rules that defy our everyday intuitions, and the simple act of measurement reveals connections that span the cosmos. Einstein wanted a local universe, a reality where information respects the speed limit of light, where causes and effects are neatly ordered. He may yet get his wish, but the price might be accepting that every quantum measurement creates entire new branches of reality, that there are countless versions of ourselves experiencing every possible outcome. Or perhaps he won't get his wish. Perhaps non-locality is truly fundamental, and we must learn to accept that the universe is knit together by instantaneous correlations that transcend space and time, connections that exist beyond the light-speed barrier. Either way, the debate that Einstein started in 1935 continues to shape physics today. His thought experiments, dismissed by many as philosophical distractions, turned out to reveal the deepest truths about quantum mechanics. His refusal to accept incomplete answers, his insistence on understanding what the theory really meant, that's what led to Bell's theorem and the experimental tests that followed. Science progresses not just through new observations and calculations, but through asking the right questions. Even when those questions seem abstract or philosophical, Einstein asked whether quantum mechanics respected locality. It took 30 years for someone to realize that question could be tested. It took another decade to perform the test, and we're still, decades later, trying to fully understand what the answer means. There is something faster than light, or there are many worlds, or perhaps something even stranger that we haven't yet imagined. The universe has revealed its mystery, but we're still learning how to interpret what it's showing us. And that journey, from Einstein's thought experiment to Bell's theorem to modern quantum experiments, is one of the most remarkable stories in the history of science. The quantum world doesn't just challenge our intuitions about how reality works. It forces us to question the very nature of cause and effect, of locality and connection, of measurement and existence. These aren't just technical problems for physicists to solve. They're fundamental questions about what it means for anything to be real. Einstein, Bohr, Bell, and all the physicists who followed them weren't just calculating equations or performing experiments. They were exploring the boundaries of human understanding, pushing against the limits of what we can know about reality itself. And that exploration continues, with each generation of physicists bringing new tools, new perspectives, new interpretations to these timeless questions. The debate is far from over. The mystery remains. But we're asking better questions now, thanks to Einstein's insight and Bell's ingenuity. And perhaps that's the real lesson. The questions we ask shape the answers we find, and sometimes the deepest truths lie hidden in thought experiments that seem divorced from everyday reality. There is something faster than light, or reality is far stranger than we ever imagined. Either way, the universe has shown us that it doesn't play by the rules we expected. And that revelation, uncomfortable and puzzling as it remains, might be the beginning of an even deeper understanding yet to come.